ATS students, Dr. John Schrage here, and I'm here to give you a little overview that'll help you prepare to do the lab in your manual that's about vertical structure of the atmosphere. I don't want to take too much time on this today because I want to make sure you have plenty of time to complete the activity, but I wanted to kind of hit on a few of the points that will help you solve these problems here. This business of vertical structure, sometimes we forget that not everybody knows what we're talking about when we say that. When we're talking about the vertical structure of the atmosphere, we're talking about how different properties of the atmosphere change with respect to height. That could be any number of different properties, like the amount of moisture in the atmosphere, or the strength of the winds, or something like that. But from the point of view of this particular lab activity, we're going to be talking in particular about how density, pressure, and temperature are changing with respect to height. Your lab manual talks briefly about how density changes with respect to height, although I don't think you actually answer any questions about that. But it's actually pretty straightforward. I mean, density is just always going to be decreasing with respect to height. Whatever the density is at any given altitude, if you go up higher from there, the density will always be less. When we're talking about density, we're talking about, like, in a volume of air, how much mass does it have? How many air molecules does it have is another way to express density, and so on. And as you go up in the atmosphere, density can only decrease with respect to height. I mean, that's why, for example, when you're climbing Mount Everest and you're so high above sea level, you have to wear an oxygen mask. The air around you, if you pull into your lungs a certain volume of oxygen, a certain volume of air, there just isn't that much mass going into your lungs. And since oxygen is only 21% of the air around us, that means there just aren't really all that many oxygen molecules in the air when you pull it into your lungs up at that top of Mount Everest. Or for that matter, if you're taking a spacewalk off of the International Space Station. I mean, you've learned about layers of the atmosphere, like the thermosphere, for example. The thermosphere extends out to hundreds of kilometers above the surface of the Earth, higher than the height of the orbit of the International Space Station. There are air molecules out there around that astronaut, just not very many per, say, cubic meter. So, I mean, if the astronaut were not wearing a spacesuit and tried to take a breath, not that many air molecules would be going in. The density of the air is just not very high when you're talking about altitudes like that. Your lab manual does go into more quantitative detail when it talks about how pressure is changing with respect to height. Now, depending on what lectures you've seen in which section of the course you're in and so on, you may or may not have learned very much about pressure yet. You're going to learn that there's a couple of different ways to define pressure and to think about pressure that are useful in different kinds of problems. But for the purposes of today's lab, the one that really makes the most sense for what we're doing here is to think about pressure as the weight of the air above you. Now, I just stole this image here from one of the printings of the textbook here because I like what they have done here, where they've illustrated this column of air. See that this is a common trick we use in atmospheric sciences to envision a column of air where, like, it extends vertically through the whole depth from the surface all the way up into space. It's a big tall column of air, and in this particular problem they want you to picture the top, like the cross-sectional area of this column is just being 1 square inch. So it's 1 inch wide by 1 inch deep by all the way to the outer space tall. Big tall column. And if you weighed all that air in the column down to the bottom at the surface of the Earth, you'd come up with a number of about 15 pounds. A more precise answer that jives a little better with both your lab manual and this printing of the textbook is to say 14.7 pounds. And actually, I mean, we should be a little more specific about this. It's 14.7 pounds per square inch. So every square inch at the surface of the Earth has about 14.7 pounds of air pushing down on it. That's one way to think about pressure. Meteorologists hate this unit of pounds per square inch. It's not very scientific. It's not a useful. It's a good unit for, like, how inflated the tires on your bicycle are, but it's not a good unit for measuring the pressure in an anticyclone or a cyclone or something like that. A better unit for pressure for purposes of meteorology is the millibar, which is abbreviated MB. And millibars are related to pressure pounds per square inch in the way that is shown here. You'll have the same thing in your lecture, I'm sure, where 14.7 pounds per square inch is the 1,013 millibars, or right around 1,000. And pressure at the surface of the Earth tends to be right around 1,000 millibars for a good round number. When you hear of somebody talking about, like, 1 atmosphere of pressure, they're talking about 1,000 millibars. But as you go up in the Earth's atmosphere, because pressure is the weight of the air above you, the pressure can only be decreasing as you go up in the Earth's atmosphere. I mean, whatever your pressure is at this altitude, it's the weight of the air above you, But if you go higher up in the atmosphere, then the pressure can only be less because there's less air above you. I mean, some of the air is now below you. And in fact, how the pressure changes with respect to height is a fairly well understood phenomenon. For every 5.6 kilometers you go up in the Earth's atmosphere, the pressure at the top of that layer, or that path, or whatever you want to say, is half of what it was at the bottom of that path where you started. So let me give you a graph over here of what pressure is doing with respect to height. You're going to be making a graph very similar to this in this lab activity today. And for this graph is illustrating this basic principle that for every 5.6 kilometers you go up in the atmosphere, the pressure is half of where you started. So like if that yellow dot there is illustrating notice that on the x-axis I've got pressure in millibars, and on the y-axis I have height in kilometers. So like that yellow dot there on the diagram is illustrating a pressure of 1,000 millibars at a height of 0 kilometers. Pretty good average value there. If I go up 5.6 kilometers, where the red dot is, if I go up to 5.6 kilometers and read over on the graph to where the red dot is, I see that the pressure is 500 millibars. It's half of what it was 5.6 kilometers below that. That actually works regardless of where you start your little path. For example, if on this illustration here, if I show you that like I had a pressure of 400 millibars, so I'm someplace pretty high up in the atmosphere, I'm a few kilometers above the ground, about 7 kilometers or something like that, above the surface of the Earth, where the pressure is 400 millibars. If I go 5.6 kilometers above that, where the red dot is, I see that pressure, if I read it off the graph, is about 200 millibars. The pressure is about half of what it was 5.6 kilometers below that. And we could do the same thing with another way up high height. This would be maybe 10 kilometers up or 20 kilometers up or something. I can't read exactly how the math worked out on this one, on my printout of these slides here. But if I go to a height where the pressure is like 100 millibars, let's say that's something like, 18 kilometers up or something. If I go 5.6 kilometers above that altitude, the pressure is half of 100, or 50 millibars. And you just keep reducing the pressure by half for every 5.6 kilometers that you go up. Notice that means you'll never actually get all the way to 0 millibars of pressure, because no matter what pressure you are at now, half of that is not 0. So no matter where you are, 5.6 kilometers up from there is not going to be 0, and 5.6 kilometers up from there is not going to be 0, and so on. The pressure approaches 0, but never gets all the way to 0 in that kind of formulation. Speaking of formulation, the lab manual actually shows you an equation for figuring out the pressure at any given height x. And I can see where this might give people a little intimidation here. The pressure at any given height x is 1,000 millibars times the quantity 0.5 raised to the x divided by 5.6th power. Alright, now, we are checking here to make sure that you know how to use your calculator to do such a thing. I mean, anytime you're raising a number to a power, you want to be using your x to the y button on your scientific calculator. Now, here you are raising 0.5 to a power that is x divided by 5.6. Okay, you could use the parentheses on your scientific calculator and raise this 0.5 raised to the open parenthesis, whatever x is equal to, let's say 1 kilometer, 1 divided by 5.6, that would be okay, or, and then close parentheses, so you first are evaluating 1 divided by 5.6 and then taking x to that power, using that, or actually do these in separate steps. First compute x divided by 5.6, write that number down, and then take x, your 0.5 raised to the whatever that number's power was. Don't be distracted by the fact that the button on your calculator is x to the y, but there's an x in this problem. Your calculator does not know how we wrote this problem here. X to the y on your calculator means the first thing I put in to the left of this button raised to the power of what's to the right of this button. Again, your TAs will be comfortable with that. They'll know how to help you with this or whatever. But you can figure out at least an estimate of the pressure at any height above the ground, x, using that that notation there. Another thing that I want you to notice in your discussion in this lab here is that we can measure the pressure at any given location, let's say 1,000 millibars. And that pressure is created by the weight of the air above you, and there's lots of different kinds of molecules above you. Nitrogen molecules, oxygen molecules, water vapor molecules, argon molecules, all the things you've been learning about so far in ATS 113. And as it happens, although, you could talk about the weight of the nitrogen molecules, you could talk about the weight of the oxygen molecules, and so on. Well, there's a rule called Dalton's Law that is that the pressure that you measure, the total pressure, is equal to the partial pressures, the sum of all the partial pressures of all those gases. The weight of the air, the total air above you, is equal to the pressure or the weight of, say, the nitrogen molecules above you, plus the partial pressure of the oxygen molecules above you, plus the partial pressure of the water vapor molecules above you, plus the partial pressure of the argon molecules above you, and so on, through all the gases. The term for that is partial pressure. The pressure of just the nitrogen molecules, or just the pressure of the oxygen molecules, or whatever. And it works out to be a fairly simple thing. Like nitrogen, for example, in the Earth's atmosphere is 78% of the Earth's atmosphere. So like at the surface, if you measure a pressure of, say, 1,000 millibars, and nitrogen is 78% of the Earth's atmosphere, then the partial pressure of the nitrogen is just 78% of 1,000 millibars, or 780 millibars. Dalton is one of the old dead white guys of science. He lived hundreds of years ago, and it's actually an amazing proof that this works and so on. But it is true that the weight, it kind of makes an intuitive sense that the total weight of the air above you is the sum of the weight of all of the different gases that are in the atmosphere. Another phenomenon that we're going to be talking about in the Earth's atmosphere in terms of the vertical structure is going to be temperature. Now, when it comes to temperature, we actually have a key term here that's an important term you're learning in this lab, and that is lapse rate. In your lab, in your readings and in your lectures, you've almost certainly already encountered the word lapse rate. Lapse rate is defined as the change in temperature divided by the change in height. As you go from one height in the Earth's atmosphere to another, you measure the temperature at one height, you measure the temperature at the other height, you got a change in temperature. Then what was the height here? What is the height here? What is your change in height? Change in temperature divided by change in height. Since change in temperature has units of things like degrees Celsius, and change in height has units of things like kilometers, degrees Celsius per kilometer is a great unit for the lapse rate. There's only one little tricky thing to work out. What do you want for the sign? Do you want the lapse rate to be a positive number or a negative number? Well, we define the lapse rate in atmospheric sciences to be positive if the temperatures are getting colder with respect to height. There's a historic reason that's actually an interesting story as to why it is that way, but again, I want to save time so you have plenty of time to do this lab activity, so I won't tell you that story right now. I think it's in your manual. Not your lab, your textbook for the class. So, like, if you have a lapse rate of, say, 10 degrees Celsius per kilometer, that means for every kilometer, at this point, at this location, for every kilometer you go up, you are cooling by 10 degrees. If you had a lapse rate of negative 10 degrees Celsius, what that would mean is that for every kilometer you're going up, the air is warming by 10 degrees Celsius. This is something we measure. We launch weather balloons with packages of instruments hanging below them, in part to measure the lapse rate. The lapse rate is really important. It's going to have a lot to do with whether or not thunderstorms happen on any given day, and things like that, and air quality, pollution, and how pollution disperses, and so on. We're not that far yet, but we will in this semester. But if you took a look at the typical temperature structure of the Earth's atmosphere, and you have this exact book in this exact figure in your textbook, and you have a very similar one in your lab manual, you can see what the temperature on the x-axis looks like with respect to height on the y-axis. And you see that there are, if you were like following with your finger up that diagram, you see that there are layers of the atmosphere where temperature is decreasing with respect to height. In other words, the environmental lapse rate is positive. And you can see that there are layers of the atmosphere where the temperature is increasing with respect to height. In other words, the environmental lapse rate is negative. We have another word for that you'll be seeing in today's lab manual. That's called an inversion. An inversion is a layer where the temperature is increasing with respect to height. But this is where we get the ideas that you undoubtedly by now have already seen in the ATS 113 lecture. For example, that lowest 10 or 11 kilometers of the Earth's atmosphere is called the troposphere. And the troposphere is that layer where overall temperatures are decreasing with respect to height. In other words, the environmental lapse rate is positive. And above the troposphere, from about 11 kilometers to maybe 50 kilometers above the surface of the Earth, is the stratosphere. And in the stratosphere, temperatures are overall increasing with respect to height due to absorption of radiation by ultraviolet radiation by ozone in that layer. The ozone layer is part of the stratosphere, but you've probably already seen that in your textbook or in your lectures and so on. And then there's another layer above the stratosphere called the mesosphere. The mesosphere goes from about 50 kilometers above the surface of the Earth to about 90 kilometers or so. And in the mesosphere, temperatures are decreasing with respect to height again. In the mesosphere, then the environmental lapse rate is again positive. Not much that you're familiar with at this point happens in the mesosphere. The mesosphere is not the most exciting part of the atmosphere. And finally, above the mesosphere, from about 90 kilometers on up, certainly to at least 500 kilometers above the surface of the Earth, you're in the thermosphere, where once again we're in an inversion, a layer where the temperature of the air is increasing with respect to height. This time because of all the crazy types of radiation from the sun and from the space environment that the air molecules up there are absorbing. So this is where those ideas, the sign of the environmental lapse rate, that's actually the technical term. The lapse rate that we're learning about here is technically the environmental lapse rate. Later on in the semester you're going to learn about other lapse rates, like the adiabatic lapse rates and so on, but we're not that far yet. So you can see how we use the environmental lapse rate, which we measure from like weather balloons and stuff like that, to determine the structure of the Earth's atmosphere into these layers. Okay, there's one more set of activities towards the end of this lab that takes a little bit of clarification, and that is, over the course of this semester in this lab, one of the things you're going to be doing is getting some experience reading weather maps. And the lab manual is not the most clear about how we're going to be doing that, and this is just our first little taste of that right here. I put that picture there of some students learning how to read weather maps from I think that's from the late 30s or early 40s or something like that. There's a great archive of these kind of pictures of meteorology students, and I thought I'd dig one of those images out. Anyway, here's what an actual weather map that a meteorologist might look at actually looks like. I don't particularly like this particular one because it's a little bit ugly, but it does have some good examples here of how we're going to be using weather maps to start getting some weather information. And if I just zoom in on one particular station here, I think that's York, Nebraska, that they happen to have plotted on this particular plot. We'll say it's York. It might be Grand Island. I'm not sure. If I zoom in onto what's York or whatever here, you see how there's a cluster of numbers and strange little symbols centered on a little circle. There are some sticks, and there's some lines, and there's some numbers, and so on. That cluster of symbols and numbers is called a station model. The word station model here refers to the fact that that is a weather station. Not like a TV station or a radio station. A weather station is like a place where there's a bunch of weather instruments run by some kind of official entity, like the National Weather Service or something. Station, in the sense that it's stationary. And this little station model is the standard notation that we use to a cluster of these numbers and symbols and so on that depicts what the weather is doing right there. And there's actually a lot of information in that little cluster of numbers, but for right now we're only going to be working about two pieces of information. I mean, that little circle that's the middle part there is actually marking on the map where the station is. And then northwest of that location on the map, there's a little number, in this case it's a 95. That 95 is the temperature in Fahrenheit. So if you are looking at a weather map, and then if nothing else, you can look to the north and the west of each of the stations there, and the number that's plotted, that's just the temperature. And you're going to need that information on the lab activity this time. Meanwhile, off to the north and east of the station, there's always a cluster of three numbers, 3 digits. And that's called the pressure code. And it is a way of getting the mean sea level pressure that is being observed at that station right now. But it takes a little bit of thinking to know how to decode that code there. When you want to decode a pressure, and again, towards the end of this lab activity you do have to do that, what you do is you put a decimal place between the second and third digits of that number there. You just put a dot there. And then in front of those 3 digits, you either put a 9 or a 10. You put whatever one it takes to make that number that you're getting now closer to 1,000 millibars. So like if you need to, well, let's do this example here. Here we have a 0.89. So we know that we've got 0.8.9, and we're either going to put a 9 or a 10 in front of that. So it's either going to be 908.9 or 1008.9. Well, whichever one of those is closest to 1,000 millibars as it happens. The 10 makes it closer. 1008.9 is closer to 1,000 millibars than 908.9, so that's the right answer. In the same way, like let's say we had the pressure code that was written there was 919. Okay, well then 919, we know we put a decimal place between the second and third digits, so it's 91.9. Then we either are going to put a 9 or a 10 in front of that, so it's either 991.9 or it's 1091.9. Well, you choose whichever one is closer to 1000 millibars, so that would apparently be 991.9 millibars. Okay, so there's some questions towards the end of the lab activity where you have to use those kinds of skills to decode a weather map. And then you're going, because it's going to ask you questions about what's going on at New Orleans or something like that. And then you look on the map and you have to make some, you have to know what the temperature is and what the pressure is at New Orleans. Okay, well that's pretty much all there is in this little activity. Again, I wanted to kind of keep, because there's a lot of steps in this lab, I wanted to make sure you have plenty of time. I hope you have good success with it. I'm sure your TAs will be able to help you, and I look forward to seeing you next week.